Okay, guys, so for the test tomorrow, I wrote the test yesterday. I think it's very reasonable. I put one sort of 6-1 problem that's just sort of like making sure that you understand that if you've got forces at angles, that you need to separate into components, right? That forces have x components, y components, and you need to solve the problems accordingly, right? So you look at all of the x motion, you look at all of the y motion. Everybody cool with that? Yeah. Okay, so there's one problem about that, and then there's a couple circular motion problem ones, and it's all the stuff we've talked about, right? Like we've done a bunch of the loop-the-loop style problems where you, like the witch's wheel one, right? Where you're going to find the centripetal force at the top and the centripetal force at the bottom, and that kind of stuff. It's infectious. I just started dancing because Maggie was dancing. We talked about the like conical pendulum thing, so you should make sure you understand that, about what happens if the force causing the circular motion is a force at an angle, like tension, or like the airplane problem. That was another good one, right? So I don't think there should be any surprises on it. I think that it's 7 or 8 3-point problems, okay? To be honest, I think it's 7, and I think I'm going to make the third one extra credit, or the last one extra credit. So that's the deal. Good? Questions? Okay, cool. So you had those last 2 problems due for today, the witch's wheel one and the spinning swings one. To McKeever's point yesterday, particularly with the swing problem, the data given to you there is experimentally determined. So depending on the methods you used, you may or may not have gotten the exact same answer that I got. But they should have been all ballpark. All right? So were we good with the swing problem? Is there anything I need to talk about on that one? Yeah.
Are we going to need to know like how to get the G's?
No, I did not put anything about that. All right. How about the witch's wheel one? Remember the last problem in the packet? I really like that one. Yeah, Sarah? Gotcha. Okay. So here's the deal. Peter came in this morning and he was asking about the exact same thing. And I pointed something out to him that he seemed to think was valuable. So let me share that with everybody. All right. So when you're on a ride like that, whether it's the witch's wheel or like a loop on a roller coaster or whatever, sort of how the forces work depends on where you're at in the motion. All right, so let's make a quick drawing of this. So, okay, so here's the circular ride. Here's the car with a little seat in it, right? And here's your person. Hello. Look how happy he is. Good? And he's spinning around this way, right? So then when he gets to the top, undo. Well, whatever, I guess it doesn't really matter. Why am I stupid? There we go. All right, so here's our person, here's the little seat, here's our dude. Can I draw an upside down stick figure? Apparently, yes. All right, so, like I said, last year when we solved these problems, the centripetal force was always provided by just one force, okay? On this ride, that's not the case, okay? So let's take a look at what's happening. And Sarah, I'm going to pick on you because you were asking about this, and I want to make sure that you get it. Is that okay? Does that discourage you from asking questions?
Somewhat, but that's
okay. I'm sorry. Thank you for being honest. Okay, so he's moving in a circle, so there has to be a centripetal force, yes? All right, for simplicity, let's assume that his speed is constant the entire time he's moving, okay? So at the bottom, point for me, what direction does the centripetal force have to act in? Upward, right? Okay. Now, here's, I think, where people get tangled up. I think a lot of times people go, oh, the centripetal force has to act upwards, and they just draw an arrow and label it FC. But the problem is this. Since my speed is constant, there's no tangential acceleration, right? In other words, he's not speeding up or slowing down. All of the acceleration is because he's changing direction, right? So the big thing that people get stuck on these problems is this. once you find that centripetal force, you can't necessarily attribute it to one force. What you should be thinking is, thank you, you should be thinking, oh, I just found my centripetal force. Because all of my acceleration is centripetal, whatever that centripetal force is also my net force. Good? So then you identify what forces are acting on your object, and then it just becomes net force equals net force.
So,
Okay? So, what were you going to say, Maggie? Sorry.
well, so at the top of it, which is real normal force, and gravity are both acting on it. So just those, like,
And I think the same thing is true at the bottom, right? So as he's moving, there's really only two forces acting on him, right? Gravity's always pulling him down, so let's go ahead and put that in. So up at the top, here's my force of gravity. At the bottom, here's my force of gravity. Good? Okay, now, so you guys told me that at the bottom, I'm going to draw it in green, my net force, and therefore my centripetal force has to act upward, right?
Correct.
Because it's got to point towards the center of the circle, right? So gravity's pulling him down. There has to be an upward force, right? Follow? So what's the upward force, you guys? Normal force, right?
we already know MC, so we can just.
So we know gravity. And then either you'll know the normal force and you can find centripetal force, or vice versa.
Okay, thank you.
Does that make sense? Everybody, does that make sense?
Yes.
All right, now let's talk about the top. The top is different, isn't it?
Yeah.
Okay? Because at the top, what direction does the net force act in at the top? Downward, towards the center of the circle. Okay? So, if the ride is going at exactly the right speed, then my centripetal force might equal the force of gravity, and I'm done. Right? If the ride is going slower than that,
You fall to the top.
then that's when you fall, right? Because gravity is pulling you down faster than the acceleration of the loop, right? And so you leave the track, right? If you're going faster than that, then there's also a normal force, right? Do you guys understand why the normal force here points down?
Yes.
The normal force is the surface of the seat pushing on his butt, right? I just said butt. Sorry, I have a 8-year-old at home and he giggles every time I say it. All right. All right. So this force of gravity is not going to change, but as you spin faster and faster and faster, your normal force gets bigger and bigger. As you spin slower and slower, it gets smaller and smaller. Once it hits zero, you might be in trouble, right? Good? Everybody good with that? Yeah.
So, from what I understand, on the top, force of gravity plus force normal is going to equal force centripetal.
Perfectly said,
But
yes.
how do I handle that on the bottom?
Same way, except on the bottom, there. So let's put in some numbers, right? So let's suppose that we've, well, here, so let me just do this. So centripetal force is mv squared over r, right? Fg is mg, right? Okay? So at the bottom, my equation looks like this. Net force equals net force. So this is all at the bottom. So at the bottom, my net force is mv squared over r. Positive, because I need it to be upward, right? That's got to equal my unknown normal force minus my force of gravity.
Okay.
Right? In other words, this guy is positive, force of gravity is negative, so your normal force needs to be extra positive. Follow? Now, when you're at the top, it's the same idea, except now net force equals net force. My centripetal force is still mv squared over r, but, well, there's something important different about the net force at the top. It's downward, right? Do you see why?
Yeah.
So I can make this guy negative, right? And then that's got to equal my unknown normal force, if there is one, minus mg. So So the only difference is this negative sign, right? Do you want actual numbers?
No, that's good.
Are you sure?
Yeah.
I'm happy to do numbers.
We're good.
Does anybody want actual numbers? I'm still standing like this with one arm up in the air for some reason. I don't know why. I'm going to stop now. Ooh, you have an arm up in the air now. What's up? Is it contagious or do you have a question? Come on, you guys. That was funny. What's up?
What's up, Brandon?
So the only thing changing in this problem is normal force?
Yeah.
Wouldn't normal force be negative though, too?
In the top one, yeah.
Yeah.
So two really good statements. I'm going to repeat those for everybody and then I'll let you finish. So what Carla just said is, so the only thing changing in this... What?
You wrote it as positive.
No, I didn't put a sign on it. So you're going to...
No sign.
No.
Then why is it
So
negative?
I was assuming... I'm sorry if this was not clear. So let me say two things. So first of all, what Carla just said is, as you go around, really the only thing changing is your normal force, right? And you need to ensure that your net force is always centripetal force directed toward the center. Okay? So that's thing one. Maggie, to your point. As I was doing this, the assumption I was making was that the thing we didn't know was the normal force. So that's like our x.
Yeah.
Okay? So x is our unknown value.
So
So you're going to do the math and solve for it. If it turns out to be negative, then that tells you it's downward.
yeah.
If it turns out to be positive, that means it's upward. When might that happen? How could on a ride like this, how could your normal force be upward?
We have to be on the bottom end of the curve.
So the normal force would have to be coming from below you pushing up, like if you had a seatbelt on. Right? Like if the ride wasn't spinning fast enough,
Yeah, so if...
then maybe the seatbelt holds you up and prevents you from falling, right?
Okay, so if gravity was bigger than normal force.
Exactly.
I mean, centripetal force than normal force.
Exactly. Good? Yeah, Carla.
Will we ever have to do anything in one of these, like, upside down things where something is on the side?
Eventually, yes.
Oh, eventually, but, like, I mean in the...
As of right now, no. As of right now, no. Good? Okay. Okay, so question about this specifically?
Yeah,
Okay, shoot.
specifically question 25B, it says your speed should be the same at the top and the bottom. Shouldn't it be the same wherever you are?
Yeah,
So why does the question just...
but just because the questions are asked later on ask you to make three body. Hey guys, please, Brendan, nobody was talking. And then, hi, how are you? Huh? Okay, cool. All right, so yes, do you guys understand that on the switches wheel ride, because it's one uniform disc spinning, that no matter where you're at on the thing, your velocity is going to be the same, right? Okay, so to your question, it says something about why are they the same at the top and the bottom. I specifically picked those points because those are the 2 points at which I want you to be able to make the three-body diagram. Capiche?
Yeah.
Okay. Anything else about the witch's wheel problem?
Has it ever, like, slowed down and, like, killed people?
Not to my knowledge, but some of those, like St. Joan of Arc fair ones, are a little sketchy, so maybe.
Did you build them?
Well, if you have to get people...
Yes.
Okay, so alright, I'm confused now with the normal force on the top equation. That's negative.
Here, why don't we just do a problem? We keep beating around the bush. Let's do it.
Mr. Hecker, if
Yeah.
you have to get people off the ride, that means at one point your velocity is going to have to be zero.
So the ride,
So they're going to have some retention.
so
bonus.
the way the ride works, you guys, is it starts out like this, and the
Oh.
things hang,
Oh.
and then it starts spinning. What do the cars do as it starts spinning? They rotate out. Then there's a big arm that goes, right?
All right.
Okay, and then they lower it back down, slow it down.
Kind of scary.
All right, so let's just do it. So here, I'm going to do two things. How much time do we have? Like no minutes, right? 5 minutes? It'll take 2 seconds. I super promise. Look,
Let's do super speed mode.
super speed mode. Here we go. So, let's make our radius be, I don't know, how about 2 meters?
Sure.
So first of all, can I figure out the minimum speed that we need to get to go all the way around?
Yeah.
Can I count it?
Thank you, yeah.
Oh,
What's that?
thank you.
Oh, 161? Okay. So, I don't know.
It's over there by around the marker. You were just referencing.
In order to get all the way around, that's got to be true, right? Your centripetal force has to be small enough to be provided by gravity, right? Follow? So the m's cancel. So I can solve for r, or solve for v, right? So v squared over r equals g. That means v is the square root of gr, right? So what's the square root of 19.6?
Let me just check that.
4.427.
427 meters a second. Good? So that's the minimum speed you need to get around it. Good? Great. Let's suppose we're going at 5 meters a second. Radius is 2. Velocity is 5 meters a second. Cool? All right, so let's see. So our centripetal force then is mv squared over r. So 5 squared is 25. Well, let's do 6, because then it'll divide more easily and we won't have to have fractions. All right, so we're going at 6 meters a second. Cool? So 6 squared is 36, divided by 2. So my centripetal force is 18m, right? Good? What's my force of gravity? mg, so 9.8m, right? For simplicity, let's just call it 10m. Is that cool?
Sure.
All right, so does everybody understand the deal? All right, so when we're up here at the top, here's what I know. I know that my net force has got to be what? 18m directed toward the center, right? Right? And I know that my force of gravity is negative 10m. So I'm totally out of room. So net force is force of gravity plus normal force, right? So my net force has got to be negative 18m because that was my centripetal force. My force of gravity is negative 10m plus normal force.
Okay.
Do the math. What do? Add 10, you get your normal force turns out to be what? Negative 8m. Why does the normal force have to be down?
Keep going faster.
Yeah, exactly. Good. I'll finish it real quick. If you have time, cool. If not, no big deal. All right. At the bottom, force of gravity is negative 10m. The difference is your net force is now positive 18m.
Yes, okay.
Cool?
Thank you.
Yep. Does that help?
Yes.
I'm around before school tomorrow. You guys have dibs on me.
Are you after school today or not?
Yep, I'm here after school too.
How did you find that?
Hang on 2 seconds. Don't go away. Let me just finish this. Net force. What did we get? 18m equals negative 10m plus Fn. Add to both sides, and your normal force is now 28m. Okay. How did I get the centripetal force?
I think there's a huge variation.
mv squared over r. So my velocity was 6.
Huge variation.
Squared gives you 36. The radius was 2. 36 divided by 2 is 18. Times whatever your mass is. M for mass, not M for meters. Good?
Why is it make the thermometer a Christmas tree?
Oh!
Like 4 tiers, like
Cool.
cool. I figured out.
Did you? I didn't get a chance to look at it
Okay,
last
we have
night.
a quiz today, so.
How'd it go, you think?
It was one question, we had 15 minutes to do it, because,